Voltage-gated sodium channels play a key role in nervous conduction by driving the upstroke during an action potential. The structure of the sodium channel directly relates to its function in the cell. Functionally, the channel has two domains: a voltage-sensing domain that responds to changes in membrane polarization, and a pore domain that lets ions through. The pore domain has two gates, the activation gate and the inactivation gate, both of which must be open for conduction to occur. Upon membrane depolarization, the voltage-sensing domain induces a conformational change in the channel, causing the pore to dilate. With the activation gate now open, sodium ions flow into the cell. But as the pore dilates further with time, the inactivation gate now becomes wide enough to be occupied by the inactivation particle, thus blocking ion flow. This is called open-state inactivation, as the activation gate was still open when the inactivation gate closed. Under other circumstances, the inactivation gate may close prematurely, before any ions have had the chance to pass. This event, known as closed-state inactivation, may occur when the depolarizing force is small and slow. Then, the activation gate is slow to open, but the time delay for inactivation to kick in remains the same, leading to an activation of the channel before it reaches the conducting state. From both open and closed types of inactivated states, the channel slowly returns to the deactivated state, in which the activation gate is closed, but the inactivation gate is open. That is, the inactivation gate is not blocked by the particle. This is the initial state, from which the cycle can repeat all over again. At the structural level, the sodium channel is made of four homologous domains that come together to form a central pore region and peripheral voltage sensing regions. Unexpectedly, the structure of the voltage-gated sodium channel reveals four lateral openings, leading from the membrane to the lumen. Lipids penetrate through these side portals, and often lie deep within the channel cavity. These lateral pore fenestrations have had important implications in medication against pain and seizure that work by blocking the sodium channel. Small hydrophobic drugs are able to gain access to receptor sites within the closed channel by diffusing laterally through the membrane. Each of the four domains is made of 6 transmembrane helices, labeled S1 to S6. Segments S1 to S4 form the voltage sensing domain, while S5 and S6 make up the pore module. The S4 helix of the voltage sensing domain has many positively charged arginine residues, which get repelled outward during membrane depolarization. This constitutes the physical basis for the voltage sensing property of the channel. As the S4 helix is repelled, it pulls tightly coupled regions along with it. This displaces the entire voltage sensing domain as a single structural unit, causing it to rotate around a hinge at the base of the S4-S5 linker. This coordinated rotation pulls the S5-S6 helices outward, causing the pore to open. Therefore, S4 movement is synonymous with domain activation. But not each of the four S4 helices is equally charged. S4 of domains 1, 2, and 3 have 4, 5, and 6 positive residues respectively. S4 of domain 4 is exceptional in that it is longer and has a high total of 8 positive charges. This confers different properties to domain 4 compared to the other three. While domains 1 through 3 activate in a single step upon depolarization, kinetic studies have shown that D4 activates in a biphasic manner. First, it is primed, and only in a second distinct step does it get fully activated. Activation and inactivation of the channel can be modeled with the help of a state diagram. Opening the channel requires activation of D1, D2, D3, and partial activation of D4. Inactivation can occur after activation of D3 and full activation of D4, without necessarily requiring D1 or D2 participation. Initially, all four domains are deactivated, meaning that their S4 regions are at rest. On depolarization, the most likely sequence of transitions is as follows. First, D1 is activated. Then D3 is activated. Next, D2 is activated. The fourth step is the partial activation of D4. This last step brings the channel to the open state, allowing ion conduction to take place. But conduction does not happen for long, as next is another activation step which brings D4 to the fully open state. This allows the channel to become inactivated, and though its activation gate is still open, it remains in the non-conducting state until repolarization. Recovery from open state inactivation takes place by the inward movement of the S4s of domains 1 and 2, which forces the activation gate to close. The inactivation particle can now be freed without leaking any current. D3 and D4 slowly recover, returning the channel to the deactivated state. In closed-state inactivation caused by small depolarizations, the channel undergoes activation in domains D3 and D4 first, making inactivation possible before either D1 or D2 has had the chance to activate. In summary, the voltage-gated sodium channel has four domains that together form two gates. Both the activation and inactivation gate need to be open for ion flow to occur. To cut off conduction immediately after a certain membrane potential has reached, nature has evolved an inactivation particle that closes the inactivation gate first, followed by slow recovery of the entire channel to the resting position.